Okay, so hi everyone, Senan this side, and in this video we are going to solve this LeetCode daily problem, which is find kth smallest pair distance. So what is a distance of a pair is basically given two integers, you take the absolute difference of those two numbers. That would be your distance. Now given an array of integers and an integer k, return the kth smallest distance among all the pairs. And yep, that is the question. So let's look at a test case. We have 1, 3 and 1. So what are all the possible pairs is 1, 3, 3, 1 and 1, 1, and their differences are 2, 0 and 2 respectively. So what would happen for k is equal to 1? We need to find the kth smallest, right? Kth smallest pair distance. So in that case this would be 0 because when you sort this the first element would be 0. In test case 2 all the elements are same, so the difference of any pair is 0, and regardless of what value of k there is you return 0. Test case 3 you would have 1, 6, 1, so the differences of 1, 1 is 0. 1, 6 or 6, 1, 6, 1 is basically 5. So if you sort them you would have the pairs as 0, 5, 5, and the third element is 5, so you return 5 as the answer. So see, there are exactly these many pairs, so k is in between this range. Now the most obvious thing is you would think of is find all the possible pairs, right? Find the differences, store that into a vector or an array, and sort them and find the kth element at the kth position. Assuming k is 1 based, you find respectively how do you do that. Otherwise what I did was, my first thought was using a priority queue which would store at max k elements. Fine. So what I do is get the size of the array and I find all the possible pairs, calculate the distance, I named it as difference. Now if I am saying, now since the size should be of this priority queue should be k, this is basically a max heap, right? So if the value is greater than, if k is greater than 0, that means our priority queue has size less than k. So I just push that element difference into the priority queue and I decrement the value of k. Now the only way this if statement becomes false is when the size, when k becomes 0, or means that our priority queue or the max heap has exactly k elements. In that case what I do is I take the top element and I check if that is greater than the difference. So this new difference could be our possible kth smallest pair distance, right? Because the kth smallest distance should be at the top of this max heap. So we need to find the kth maximum element in this heap, right? So I push this and I pop this. Otherwise if this condition is false I won't even push that into my priority queue or the max heap. In the end, after I check all the possible combinations, I just return what is at the top of the element. So this should work and this would work, but there would be a time limit exceeded issue. Why? Because let's discuss the time and space complexity of this. The space complexity, since we are using priority queue, would be big O of k, and k at max could be n times n minus 1 by 2, so order of n square. So the space complexity is order of n. Again, at the same time, the time complexity is also big O of n square because we are using two for loops, right? We are iterating to all the elements twice, or basically we are finding all pairs, so basically we are getting a time complexity of big O of n square. Okay, so this is giving me a time limit exceeded. So can we improve this? And the answer is yes, we can. And what logic should we use? Since we need to find pairs, we need to at least see all the elements once, right? So at the worst case, we could possibly have a big O of n solution, which would not be the case. We know that we cannot go better than big O of n because we need to see at least all the elements to find a possible pair, right? And we just discussed the n square is not working. So what is the possible approach you could think of? It's n and between n square, so we can see, or we can try to think of an n log n approach, something like that. So that gives me the hint that I need to do something with log n. So that is what we are going to use. We are using binary search on answer. Now I would explain this, and after that I would go to my notebook and I would show you a test case or a dry run that what we are actually trying to do. Basically the dry run of this count elements, because that is the most important thing you need to understand in this code. Now basically I sort these elements. Why do I sort this? Because for this function, to make this an efficient version of counting elements, we need to sort. We'll see why this helps later on, but we have to sort. So this takes n log n time first and foremost. Now what is the binary So since we are using binary search, we are assuming that we have a sorted array, hypothetical array, but a sorted one. So what can be the minimum value of distance? So the minimum value could be 0 because you can have two of the same elements and we are using absolute value. So 0 at max can be the worst case or the best case, whatever you call this. 0 could be the minimum possible answer of this binary search. What could be the maximum possible difference? I'm not talking about the kth smallest or kth largest. I'm just talking about what is the maximum possible distance, and that is basically the largest element in this nums and the smallest element in the nums and the and since I have sorted this would always result in a positive value, and this would be the maximum difference you could actually attain. Now the question is, or not the question, but what we want is a value in between them, right? Okay, so we are going to find a number between this left and right inclusive of both the elements, and we are trying to find a number such that that is the kth smallest pair distance. Now what I do is basically the basic binary search is you calculate the mid value, right? And you call this function and you do something, otherwise you do something else. Now what this count elements does, so given this array, it takes a value mid and finds the number of elements such that, or number of pairs of elements such that the difference is less than mid. So for example, if the mid value is say 5 and I go into this nums array and find all the possible number of possible pairs such that the distance between them is less than 5. So if that is greater than k, that means this mid value could be a part of our answer, or value less than mid could also be a part of our answer. So that is why I take right is equal to mid, not mid minus 1, because this mid value could also be our possible solution, because we could have duplicate elements and all sorts of things could happen. So that is why right is mid. Otherwise, if count elements nums and mid is less than k, that means given this mid value, we cannot find number of pairs such that their difference is greater than equal to k. That means that mid value cannot be our answer because we cannot find k pairs such that their difference is less than mid basically. So that is why that is not a part of a solution. So I put this left to mid plus 1. And now the whole point of this is how do you actually count the number of elements, right? In the previous case, we as you saw, we did a two for loops, right? That resulted in a time complexity of big O of n square. So can we do in a more efficient manner? That is, yes, basically since we have our array sorted, we can count the elements or count the number of pairs such that their distance between them is less than equal to mid. So let's look at this count elements function. So I initialize the first pointer. So basically we would be using a two pointer approach. I would be the first pointer, j would be the second pointer, and remember j would always be ahead of I, and we take n as the size of nums, pass this reference and not by value. And while j is less than n, that means we have a valid index. So what I do is I increment, so I keep track of number of elements and I check if nums of j minus nums of I is less than k, or this mid value. I can change this to mid. So if nums of j minus nums of I is less than equal to mid, that means this is a valid pairing, right? This is a valid pairing. So what I do is I add that to my other count plus equal to j minus I. We'll see why j minus I in the notebook I would show you after this explanation, and I would increase the value of j. Otherwise, I would increase the value of, and in the end, after doing this, I just return the count. Okay, so let's first of all, I just comment this out and see if this is working fine or not. Okay, so it is accept beats 83.60, but that is fine. Now let's look at the notebook and see how are we actually counting the number of elements, or how is this working. Clearly, before we go there, since we are iterating once over the loop for j and I, basically we have a time complexity of big O of n. So this is a linear time complexity solution, and binary search would take what? Log of max value, that is this value, log of this value, and count of elements for each time. When we call this binary search method, we are doing big O of n operations. So the time complexity for this case would be n log max difference, plus we are also sorting this, so n log n. So that is the time complexity. Space complexity is basically constant. We are not using any extra, nor that I see one. So yeah, let's look at the notebook and see how this count elements function actually works. Okay, let's look at this. You have a list of sorted elements and be, this is basically your nums, and the mid value is 4. Now I need to count all the pairs as that this is 2, right? So the iteration I would be, or the two pointer approach that I would be using is, so I check if the value of 1 and if the value number 3, nums of j minus nums of I is less than equal to, let's say mid is 4. So if this is true, right, I would say that this is true, this pair is a valid pair, so I would increase my count to +1. Now what I would do is I would take this j and I'll place it one step ahead. Now I see that is 5 minus 1 less than equal to mid, which is 4. That is true. 5 minus 4, 5 minus 1 is exactly 4. So 4 is less than equal to 4. So I see this. So what did I do? J minus I, right? Let's index these elements 1, 2, 3, 4. So what is j minus I in this case? This is j minus I is 2 minus 0, that is, so I would increase +2. And what this is taking in consideration is why this 2. So since this minus this is less than equal to 4, that means this minus this is also less than equal to 4. Why? Because these elements are sorted, so any element after 1 would be greater than this, and since this number is greater than 3 is greater than 1, so the difference between 5 and 3 would be less than equal to 4, right? So that is what we are trying to, when we were at 3 we were taking this consideration, right, this pair. So that is this. Now since we are at 5, we are taking a pair this, so 1 and 5 is also considered, and 1 and 3 is also considered. That is why j minus I. Now since this is true, what I would do is take this j, place this one step ahead, and again I would check if this condition is true. So nums of j is 6 minus nums of I is 1, so that is 5. 5 is not less than equal to 4. So I don't do anything. What I just do is I increment the value of I. Now I do the comparison. So is 6 minus 3 less than equal to 4? That is true, because 6 minus 3 is 3. 3 is less than equal to 4, so this is true. So what I would do is I would increase, so 3 minus 1 is 2, so I would increase this to 2. And what would happen now is we are considering the pairs 3 and 6 and 5 and 6. 6 minus 5 is 1, 6 minus 3 is 3. So we are considering these two pairs in our solution. Now since this is true, what I do is I take this j, I place this ahead, and I again compare. So is 10 minus 3 less than equal to 4? That is false. So I would take this I, move step ahead. Again I would compare, is 10 minus 5 less than equal to 4? Again that is false. So I would take this I, place the step ahead, and I would ask, or is 10 minus 6 less than equal to 4? That is true. So 10 minus 6 is exactly equal to 4. So what I do is I do j minus I. So j is 4 and I is 3. So j minus I would be what? 1. So I would add 1 to my solution. After that, my j would point to a index which is beyond the size of the nums. So I stop my function, or we break out of this while loop. Now what I would do is basically add these all up. So 1 plus 1 is what? Is 6. So what this did exactly is, given this array of sorted elements, I counted the number of pairs whose difference or whose distances is less than equal to this mid value. And to do this, we did a linear search. Basically, we took j, I and j pointer, and we just slided j, 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 j once, and I, and I. So you are moving j and I at least and at max once throughout the list. So this would be giving you a big O of n time complexity, and space is constant because you're not allocating anymore. Apart from the nums array that is already given, I'm not considering that. So basically, if my possible solution is from left and right, incorrect spelling, right, so my answer is somewhere in between this. So I am at this position, and I would say this is my mid. I say count elements of I pass this nums and the mid value. So what this would give me is, can I possibly have at most or at more than or equal to k elements at this mid value, right? So if that is possible, my difference, the kth maximum difference, would be before this or could be equal to this if this condition is true. So I would reassign the right to mid value. If that is not the case, I would take this left value and I point it one after the mid value, because mid possibly not be the answer, because at mid, when we assign left to mid plus 1, in that case we mean that the value of this is basically less than k. So we cannot possibly have the difference as mid, because we would have less than k elements. We need to have k elements, right? So that is the whole point of this video, or the whole explanation. Hope I was able to explain you, and Yep, thanks for watching and bye.